Welcome to a lesson with Dr. Powell. Let's look at an example of trying to determine if three vectors are linearly independent or dependent. What does it mean for three vectors to be linearly independent? That means that there's one and only one way of having a linear combination of them that equals 0, 0, 0. So the zero vector over here. And that one way is to make all these scalars right here, this A, B, and C, to make those just zero. That definitely would work, but is that the only way of doing so? Now, if that's the only way of doing so, actually, there's only one way of doing that for any vector over here, not just the zero vector. So just checking for the zero vector means that it will work for any vector, really, which means that if we use these vectors themselves in space as determining like three different axes, and you kind of get a skewed type of coordinate system with these, like this and like that, and you can kind of draw a unit box, which is like a unit parallelepiped in here, and you stack these this way and that way and whatever else, you get this whole coordinate space that's kind of skewed in some way or another, but you can still map out coordinates. These scalar coefficients would be like a plot along this axis, where the unit length along the axis is actually just the vector itself. And then you kind of plot this guy on that axis, this guy on the other axis, that guy on that axis, and then you go to a particular point. And so every point would have exactly one and only one way of being represented in this coordinate system. That's another way of thinking about what it means to be linearly independent. If these three vectors were linearly independent, then they would span all of three space, meaning that every single point could be described in such a coordinate system. Okay, that's one way of thinking about it. So that's what we're trying for. And what we do is we just take this and we say, okay, what are all the A's, B's, and C's that actually make this work? Well, we can determine that by a system of equations. Simply multiply the A here, the B here, the C here, and then like add across this one component right here. That's what this is. 2A plus B plus 3C, and that's equaling 0 right here. So the first component there must be 0. And then you can do the same thing for the next component, 3A, 2B, 5C added together should be 0. And down here, you should have negative A plus B, that's just 0, so is equal to 0. So we have a system of equations, three equations, and three unknowns. Now, let's think about this in another way. This is the same thing as having a function that goes from R3 to R3 defined like this, where this is like the first, like the output in the first component, the second component, the third component. I just kind of copy these right here. So this is, I get it ordered triple. So I take ABC, ordered triple in R3, and it outputs an ordered triple in R3. So this is a function. In fact, this is an additive function. And what we're trying to do is we're trying to say, when is the output equal to the 0 vector, is what we're trying to show. When is the output here is equal to the 0 vector. That's the same thing as looking for the fiber over the 0 vector in R3. So the fiber over 0. So everything that maps to 0 in this function. Now we had a criterion for this, which was that the criterion for this is that this function is injective, because this is additive, precisely when the fiber over 0 is only 0 itself, or only has one element in that fiber. So if there's only one element in this fiber, then all the other fibers have only one thing in them, which is exactly what we were saying before. We wanted this output to be anything. There's only one and only one way to get that. And that's kind of like looking at a fiber over the vector that we're interested in. There's only one way of getting it. So that's really what linearly independent shows. And it shows it because we have an additive function here, and all the fibers of this additive function are simply shifts of the 0 fiber. So hence, it just suffices to check the the case that we're over 0, just the 0 fiber, that's enough to see that this will actually work and hold. So, and then we would know that they would be linearly independent. In at least with that description, that there's only one and one way to represent coordinate points in terms of those. So however we want to think about that. Okay, so let's get to it. Let's actually see if we can see what this fiber looks like. And as soon as we know what it looks like, we'll know if this really is linearly independent or not. If this fiber only has the 0 vector in it, then we know that these are linearly independent. And if it has more than that, then we know that they are linearly dependent. Okay, so if we'll look at this last equation right here. This actually tells me that B is equal to A. And so from that, there's various ways of approaching this, but maybe this time through, let's just replace all of our, well, yeah, sure. Let's just replace all of our A's with B's. So then that would tell me 2. So we could just literally just write it in 2B and 3B. So that would tell me on the top, that would tell me 3B plus 3C equals 0. On this one, we'd have 5B plus 5C equals 0. Notice that these equations are the same equation. There's no difference of them. I mean, this one right here is just 5/3 times the top one. So really, we just have this equation, which simplified, dividing it by 3, just looks like B plus C is equal to 0. So, which tells me that B itself is equal to negative C. In fact, all the solutions to this system of equations look like this. C looks like has no restriction on it. It can be anything it wants, but B depends on it. So B would be negative C, and A is the same thing as B, so we could just write down a negative C. So all the solutions are this form, and you can check it. You can actually find, if you put in a -1, -1, 1, you'll actually see that that's a solution. You could try it out here, like -2 minus 1, that's -3, and then +3. Oh my goodness. So it works there, and you can check through all of them. It works. So, already, -1, -1, 1 is a solution, but you also knew that 0, 0, 0 was a solution here. So this fiber has more than one element. It's not injective. It's not linearly independent. So we found an A, B, and C. That's all we needed. We just need to find one of them, and we did. We found an A, B, and C such that we get a linear combination that's equal to this, where A, B, and C were not 0. So therefore, we know that this set of vectors is linearly dependent. Thanks for watching.